All right, here's practice problem number 4. What is the surface temperature of a star if its peak wavelength is 644.4 nanometers? And B, part B, what is the stellar spectral class? So you have to look at this table. When you're taking the test, just make sure you have this table, which is in chapter 13, 13.3. All right, anyhow, we use Wien's law, right? So this is Wien's law. The temperature in Kelvin is equal to this constant 2.9 times 10 to the 6 divided by lambda max. So there it is. I mean, this is a very easy problem. So this is for part A. This first thing, this is for part A. If the answer comes out to be 4,500 Kelvin. Just remember, the temperature of the sun is at 6,000 Kelvin. So this is a star that's cooler than the sun. And if you look up on that table, part B, the table will clearly show that this falls in the range of a K-type star. This is a K star. K star. I'm not supposed to say star. All right, so yeah, so that's that one. All right, let's move on to number 5, and here's problem number 5. I forgot to erase that right there. Sorry. So this is problem number 5. There, let's erase that little part. All right. So it says Saturn has a radius, and they give us the radius of it, and its mass is 5.68 times 10 to the 26th kilograms. Find the Schwarzschild radius. And so to remind you, the Schwarzschild radius is the size something has to be the size something is going to be if it's a black hole. Now remember, Saturn is way too small to ever become a black hole, but using Schwarzschild's radius doesn't really distinguish between massive stars that have collapsed and become a black hole. It's just a short, simple way of calculating the size of a black hole. I mean, it is accurate, but just keep in mind, Saturn is not such an object that will ever become a black hole. So there's nothing that can crush it down to this size. All right. Anyhow, if there were something to crush it down, how big would that thing have to be? What would be the radius of it for if you could somehow crush this incredible mass down? Then notice in this problem they gave us the actual size of Saturn. That has nothing to do with the problem. All right. So the only variable is really the mass, and the mass has to be in kilograms, which it is right here. So you just do this 2 times big G, 6.67 times 10 to the minus 11th times the mass of Saturn, 5.68 times 10 to the 26th divided by the speed of light, 3 times 10 to the 8th squared. So when you do that, you get, let's see, on my calculator I got 0.84 meters. So that, which and that's the answer, right? So that would be the size of if you could squish Saturn down so its radius was only 0.84 meters or 84 centimeters in radius, then it would turn into a black hole. But again, there's no mechanism for that to ever happen. All right, let's move on to number 5. I'm sorry, number 6. All right, so here's problem 6. We want to calculate the escape velocity and the density in grams per cubic centimeter for a neutron star. So actually, I'm going to do. Let me relabel this. We're actually going to do part B first. Sorry, let me erase that real quick. So we're doing part B. Just because that's just the way I started it. So notice the mass is 1.6 times the mass of the sun. So there's the 1.6. The mass of the sun is 2 times 10 to the 30th grams, and of course, 2 times 10 to the 30th kilograms, and then 1 kilogram is 1,000 grams, or 10 to the third grams. So this becomes, when you multiply all this stuff together, 1.6 times 2 times 10 to the 30th times 10 to the third becomes 3.2 times 10 to the 33rd grams. All right, so that's the answer in grams. And then notice they give us the radius of the neutron star. It's 29.5 kilometers. You might remember how to change kilometers to centimeters. Let me do that real quick. If you didn't remember this, in one kilometer, there is 10 to the fifth centimeters. All right, you can actually work that out step by step, but if you remember that, that's perfectly fine. So this, of course, becomes 29.5 times 10 to the fifth centimeters. And so really now the only thing we have to do is, well, there's two more things we have to do. One is we have to calculate the volume, which of course is 4/3. Yes, that's right, 4 pi over 3. 4 pi over 3 times r to the third. So I'll just put, what r is here. It's going to be 29.5 times 10 to the fifth. And of course that's in centimeters. So, and then we cube that. That's going to be cubic centimeters. All right, so let's see what that comes out to be. Let me see. So 29.5 times 10 to the fifth raised to the third times 4 pi divided by 3. All right, so I get 1.07 1.075 times 10. That's supposed to be a 5 times 10 to the 20th. Centimeters cubed. And so what we're going to do is we're going to take this number and we're going to divide it by that number to get the density, right? The density, I'll do that down here. So remember, this is part B. The density of the neutron star is going to equal, so it's 3.2, that 3 didn't come out very well, 3.2 times 10 to the 33rd, divided by, and that's grams, divided by this 1.075 times 10 to the 26th, and that's centimeters cubed. All right, and so our answer comes out to be, let's see, I got this already in my calculator, so it's going to be 3.2 times 10 to the 33rd divided by answer. I get 2.97. It's close to 3. It's 2.97, so I'm just going to put 3 times 10 to the 13th. 10 to the 13th. And that's, of course, grams per cubic centimeter. Centimeters cubed. All right, so that's part B. I'll have to go to the next slide to do part A. Part A, we're just going to calculate the escape velocity. So we just need the mass in kilograms. So we're just going to multiply 1.6 times 2 times 10 to the 30th, and we're just going to convert 29.5 into meters. So instead of K, it will be times 10 to the third. All right, we'll do that in just a second. All right, so here's part A, calculating the escape velocity. So remember of course, the escape velocity equation is the square root of 2 times g times m divided by r, where m has to be in kilograms and r has to be in meters. So they give us that the mass of the neutron star is 1.6 times the mass of the sun. So that so let's see. Let me just make sure. 1.6 times 2 times 10 to the 30th. That way I already have it in my calculator. So it's, I already wrote it down, 3.2 times 10 to the 30th. And so that's the mass, so I can actually write that in here. So that's 3, oops, let's go back to this. Okay, so that becomes 3.2 times 10 to the 30th doesn't really look like it's coming out too well. That's 10 to the 30th. And then the whole thing is going to be divided by, all right, so now we have to change the radius from kilometers to meters. That's what I did right here. So 29.5, and then in 1 kilometer there's 1,000 meters, so it would be 29.5 times 10 to the third, right? So let's put that in the denominator. Remember, this is all under the square root. 29.5 times 10 to the third meters. All right, and so we'll do the calculation here. All right, so I just put this in my calculator. All right, so this turns out to equal, here, it's kind of hard to write right here. Here, let me go to the next screen, sorry. All right, so here we go. So the escape velocity, that's what we're looking for. And remember, it's always in meters per second. Turns out to be 1.2, and it kind of keeps going, right? 1.2029. All right, so I'm just going to change it into scientific notation. So let me move the decimal place to the left. So 123, 123, 12, times 10 to the 8th. 10 to the 8th meters per second. It's good to know. So remember, this was part A of that problem. It's good to know that as well, or something to note, is that this now starts to approach the speed of light. Recall, the speed of light is 3 times 10 to the 8th, and there's nothing faster than the speed of light. So, trying to leave the surface of a neutron star, you're really approaching the speed of light. Of course, trying to leave the surface of a black hole, the escape velocity is the speed of light, right? That's kind of the whole point of that one, of black holes anyway. All right, let's move on to the next problem. All right, here's number 7. This is using the Doppler shift. It says the spectrum of a star is observed, and a wavelength of the moving star is measured to be 730.5 nanometers. The same wavelength is measured in the lab. So that's the lambda naught is 730.8 nanometers. How fast is the star moving, and is it moving towards or away from us? And remember that so this delta lambda, which is the moving wavelength minus the rest wavelength, or the wavelength in the lab, if that turns out to be positive, then that means it's moving away from us, or it's red shifted. If it turns out to be negative, that means it's blue shifted or moving towards us. All right, so and also generally with this particular formula, we use the speed of light to be 3 times 10 to the 5th kilometers per second, and usually that's a typical thing, measuring the velocity of things in space to be in kilometers per second. It turns out to be a more unit friendly number. All right, so when we do this, the moving wavelength is, notice that everything's in nanometers here, so nanometers minus nanometers divided by nanometers. This first thing, the delta lambda over lambda naught, the units will cancel, and so you're just going to have some fraction of the speed of light. Anyhow, the numerator part is the 730.5 minus 730.8, so you can see already that that's negative. Therefore, if it's negative, of course, that means it's moving towards us. It's blue shifted. All right. The amount it is, when you do that, it turns out to be negative 0.3. So it's going to be, so the velocity is negative 0.3 divided by the rest wavelength, which was 730.8. That's supposed to be a 3 right there. And of course the nanometers cancel. So this was nanometers, this was nanometers, and they cancel. And then multiply it times the speed of light, 3, but you use the speed of light in kilometers per second, so 3 times 10 to the 5th kilometers per second. All right, and that turns out to be negative.